In this video, we're going to complete our investigation into transformations. However, we're going to start off the video by looking at a student question around circular functions. Enjoy. So the agenda for today is to have a look at the remainder of our transformations stuff, where we're looking at determining a sequence of transformations. But before that, there was a student question to get into, and so we're just going to briefly review how you would solve, or rather sketch, circular functions when there are both horizontal translations and vertical translations involved. So we'll cover that briefly. First things first, when you have horizontal translations, one of the things that comes up is the fact that your key features, your middles, peaks, and troughs, all need to be shifted in a certain direction. Right, if you have x minus a value, you're going to be shifting all those key features to the right. If you have x plus, you're going to be shifting all those features to the left. So normally when you do your division of the period, when you quarter up that period, you now also have to add or subtract a horizontal translation to accommodate that. As part of this, you may or may not also have to additionally find a y-intercept, because that will no longer be one of the key features you solve just by doing your quarter period. Although in this circumstance here, there was no y-intercept to be found, so you may or may not have to find it. Additionally, if you have a vertical translation, in the best case scenario, it actually becomes easier, in the sense that you don't have to solve anything else, right? It never touches your axis anymore. However, in a worst case scenario, you now also have to find additional x-intercepts beyond what you would have found from your quarter period formula. And so you solve those like you would for any other x-intercept, which is y equals 0. So I'll go through one of these using the framework I outline here, which is we're going to have -2 cos x plus 1. We're going to just solve that. First things first, you want to find the period of your circular function. So period is always 2 pi divided by n. In this case, you've got n equals 1. So period is going to be 2 pi. From there, peak and trough. Because you have a vertical translation of 1, not only is the peak and trough going to be plus minus 2, but it's also going to be shifted up by that 1. So yes, you add and subtract 2, but you're doing it from 1 rather than from 0. It's going to give us a peak of 3, trough of -1. From there, you divide the period up into 4 equal parts. The period was 2 pi, halve it to pi on 2, and then backfill. If you have a horizontal translation, this is where you would adjust these. So if this was like a plus pi over 3, then you would shift all of these back by pi over 3 by doing a subtraction. And that would be kind of painful because you have to adjust all the bases, but or rather adjust all the denominators, but that's what you would have to do if there was a horizontal translation. Yeah, and then once you've done that adjustment, if need be, you dot out the overall shape. We had negative cos, so it would start at a trough rather than at a peak like it normally would. Trough, next one should be a middle, next one should be a peak, so on and so forth until you fill out that first cycle. What you'll notice is that we now have additional x-intercepts to solve. As I said at the beginning, you take whatever your function is, set y equals 0. You solve that circular function by referring to the unit circle, and then you put those on there. I do have a few key questions for us to go through on this one, but before that, are we clear on the process? Because if not, I can clarify that a bit.
It froze for a little bit, so is it possible you could go through it again?
Where did it freeze, sorry?
Like my video just froze and I missed out on the part where you explaining.
Explaining from like the very beginning? Uh-oh.
Yeah, sorry.
Cool. How about I'll do it with one of the examples that we have here that haven't been pre-solved. That way everyone can be doing a slightly different version of it. But basically,
Yeah.
we're going to be following these steps. Is the screen all good now to follow?
Yeah, it's all good. Thanks.
So I've got a screenshot of that if you also want to use it from the chat. So if we have a look at this example here, if it decides to focus, I guess that's what we're getting today. First things first will be finding the period of this circular function. And so period being 2 pi divided by n, 2 pi divided by n, really can't see that. Why won't you focus? There we go. So n in this case, what are we looking at for n? Pi. Yeah, the period overall will be pi, correct? As far as the n value itself, that would be the coefficient on the, in this case, t. And so you'd do 2 pi divided by 2 for a final period of pi. Yeah. 2 pi divided by 2, period is pi. Yeah. Cool. All right, that's step 1 done. Next up is find our peaks and troughs. So how do we do that? Peak, trough. Spelling lessons today. Probably also worth having the generic circular function up here, which is any circular function would look something like y equals a sine n bracket t minus h plus c. So that will tell you what all the terms are. So if you're looking at the step 2 and you think peak and trough is c plus minus a, well, there's your c and there's your a. So if you refer to the red one, the one we're doing, what would our peak and trough therefore be?
Chris, would it be the peak? Would the peak be 4 and the trough be 0?
Yep, absolutely. Our c is 2, our a is 2, 2 plus 2 is 4, 2 minus 2 is 0. Nice. All right, step 3 is divide the period into 5 equal x coordinates, which means quartering the period up, and it ends up being a quartering, but the reason why is because 0 counts as a value there. So period was pi in total. If we were to quarter this up, what would all of our intervals be in terms of as far as like gaps between them? Pi on 4, correct. Halve it again. So I'll zoom in on that just a little bit more. Pi on 2 would be there. Pi on 4 would be there. And then 3 pi on 4. Nice. And reminder that 0 counts as one of those values. Okay, cool. Adjust the x-coordinates by our horizontal translation. So we do have a horizontal translation here. I will say this, where this question came from was CAS, so we won't have to necessarily do all the arithmetic by hand for this. What is our horizontal translation? And based on that, what would we have to do to our x-coordinates? I noticed you just left it and joined. I'll state the question again, which is we now have to adjust by our horizontal translation those x-coordinates we just found. What is our horizontal translation, and therefore what would we have to do to fix them up?
We have to like add pi over 3 to all the coordinates.
Yeah, correct. We're just going to add pi over 3 to all of them. So I'm scared of moving the camera away so it doesn't defocus. But off screen, I'm literally just going to add pi over 3 to all these values. So 0 plus pi over 3 is of course going to be pi over 3. In fact, maybe what I'll have to do is take these off the axes just so I can remember them all. Pi on 2, 3 pi on 4, and pi. Those will be the remaining ones. And so these ticks would now become pi over 3 greater than that. It's a little bit bigger. I'll put that there. Okay, 0 plus pi over 3 gets us to pi over 3. Pi over 4 plus pi over 3. That's pi. 7 pi on 12. And then, actually even from here, this would just be a repeated addition of pi over 4 anyway. So I guess we could just do that. Plus pi over 4. Get us to 5 pi over 6. Do it again. Plus pi over 4. Get us 13 pi on 12. And if I've done this right, yeah, the last one's 4 pi over 3, which is what we would expect if you were to add pi over 4 to pi. Oh, sorry, if you add pi over 3 to pi, you get 4 pi over 3. Cool. All right, so that's us having adjusted all those key features now. From there, finding the y values at those spots by referring to just what sine or cos naturally is. So this one's a positive sine, which tells us what exactly, where does it start? Peak, trough, or middle?
Does it start at 2?
Start at 2? Yeah, because it starts at the middle. Yeah, so our middle, which we didn't really clarify, is just going to be whatever the vertical translation is. And so the fact that it starts at 2 means the starting coordinate would therefore be what?
Do we start it from pi over 3, and then like first finish it towards the right and then continue it to the left after we finish the original one?
So potentially you could go to the left, but we're sketching over this specific domain here. So starting at pi over 3 is correct. Going backwards, if you were to refer to the domain, you would notice that you actually have already started exactly where it's telling you to sketch over. But yeah, so this will start at a middle. And then from there, do we go to peak or do we go to trough afterwards when it's positive sine? Peak, yeah, that's it. And then the rest of the pattern should be obvious from here. It's got to go back to the middle, then the trough, which thankfully actually is a good vertical translation for us because we don't have to additionally solve any x-intercepts in this case. From there, just join the curve. I'm going to make it green just because it's probably a bit easier to see with green rather than red. And double check that you've done it through the domain. So pi over 3 to 4 pi over 3, we've achieved exactly that. Just like your approach says, if you did have a different domain, then you would go between, you would just keep like subtracting pi over 4 backwards or adding pi over 4 forwards until you fill out whatever that domain is. If you had to find additional x-intercepts, then all you would do is go through and set y equals 0 on this. This would be a CAS question, so it would literally just be set this, solve for y equals 0. If you were to do it briefly by hand, then let's see. Yeah, I'll do some of this by hand. I'm just going to briefly rewrite it over again. So 2 sine 2t minus pi on 3 plus 2 equals 0. Okay, set that equals 0. Subtract 2 from both sides and divide by 2. You're looking at where sine of 2 bracket t minus pi on 3 is equal to -1. So subtract 2, divide by 2. Now, yeah, this will be the same thing. We won't have to have a look at this one. From there, you would do a substitution. So you would just plug in u into here. And when it's sketching, you don't really have to worry too much about your new effective domain because you can already see where the solutions are likely to be. Like this one here, off the bat, we can see we're only going to expect to have one solution. From here, we just got to remember where is sine equal to -1. Anyone remember what angle gives you -1 for sine?
Is it like 3 pi over 2?
Yep, 3 pi over 2 is correct. So u equals 3 pi over 2 would be one of the solutions. You could obviously add or subtract 2 pi to get multiple, but we can already clearly see we're only looking for one here. So that's one of the advantages of having the sketch there. But we don't want a u solution, we want a t solution. So you'll do 2t minus pi on 3 is in fact equal to 3 pi on 2. So just replacing that u with what it actually was. And then from there, if I've done my math correctly, rearranging for t should get us the value that we had before. T equals 3 pi on 4 plus pi on 3. T equals, I think these 9 pi plus 4 pi on 12. 13 pi on 12. That sounded good. And sure enough, we got it. So obviously that's a bit of redundant work. It's more so if your circular function happened to dip like that, then you'd have to worry about those spots. Cool. All right, that's how you would handle that. The second question that I had there was very, very similar. It was just a cosine, but for the same sort of idea. Cool. Okay, that's our brief revision on circular functions. Now, for the agenda, back to transformation stuff. So, in the previous version of this class, we had a look at the transformation fundamentals, which was essentially how do we apply a sequence of transformations to a particular existing function. And one of the more effective ways of doing that was through the point form or the point notation version of that working out. We'll focus on that mainly as well for this one here, although we will also look at the alternative approach, just in case you were at all interested in doing that. My personal recommendation is the point version. But okay, literally all we're doing here is doing the reverse of what we did in our applying transformations. When we're applying transformations, we want to figure out our x dash, y dash from that, and then rearrange it so we can plug it into a function. In this case, we're trying to take it out of a function and then get it back to whatever the transformations are. So, I've got a couple of examples here. The whole point is not that they're different, but that they're the same, which is the sense that it doesn't matter if you go from transformed to untransformed, or the other way around, or even if they're both transformed, you still follow the exact same procedure. So, from here, find a sequence which maps f to g. So you want to figure out, well, step one is just figuring out where are we starting and where are we going. The point where you're starting is going to get x and y notation. So instead of saying f equals all this, we say y equals all that in terms of x. The place where you're going is going to get the x dash and y dash. So in this case, instead of saying g of x here, you're going to say y dash is 1 over x dash all squared. That's step one, getting our bearings as to notation. Next up is to make sure that all the transformation factors that are affecting the y will go on the y side and everything else will stay on the x side. So we got a vertical translation of 6 and a dilation factor of 3 from the x, or along the y. So we're just going to rearrange for that. Subtract 6, divide by 3, that's going to get you that. If you have trouble identifying what's a y and what's an x transformation, the very basic version of this is just rearrange this until, rearrange this without touching the x stuff. So here's the x thing, rearrange everything but that. That's kind of the basic rule there. Ideally, you would know what each of the transformations do just by looking at the terms, but while you're still learning it, that's a basic rule to follow. You will do that for both functions. So this one has transformations, you definitely want to rearrange that. This one just didn't happen to have any, but if it did have some y transformations, you would also put that to the other side as well. From here, we're in a stage where we can now compare the two functions together. what we do is we look at the y stuff on one side and compare it to the y stuff on the other side. So we got y minus 6 over 3 for the first function, and we got y dash for the second function. We equate those two things together. This finally gives us an equation comparing y to y dash. We do the exact same thing for the x stuff. So there's only a translation of 1 here, and there's no transformation here. That's just going to give you x minus 1 is equal to x dash. Now again, if you get confused on exactly what you should take from the x side, you could also just rip the entire right-hand side and call it a day. Like you could do 1 over x minus 1 all squared equals 1 over x dash squared. That also works. It just means it's a bit more working out as far as getting x dash back on its own. Because this final step here is to make sure you have x dash and y dash on its own. In this case, they're already on its own. If you happen to have ripped this directly from the right-hand side, it would look something like this, which I'll do on the handwritten bit. You would have 1 over x minus 1 all squared equals 1 over x dash squared. And of course, it's not focusing. There we go, that's better. Then from there, to get x dash on its own, you would do a bit of a cross multiplication. So multiply both sides by this denominator, multiply both sides by this denominator. Or you could also just like compare the fractions, right? There's 1 on top here. You can pretty quickly just go x minus 1 all squared equals x dash squared. However you want to think about it, you'll get there either way. And then from there, to free the x dash, you would just square root both sides. X minus 1 equals x dash. That gets you back to where we could have started if you would, once you get much more familiar with what actually you need to pull, which is just the transformation factors, not necessarily the entire right-hand side or left-hand side. But okay, at this stage we have our x dash, y dash. That means we've determined our transformation. That's pretty much it. You've determined your transformation. That's what this is all aiming towards. However, a lot of the time, your book or SAC will ask you to express that like in a written sentence, what those transformations actually are. So it's all good to have x dash, y dash. We now need to put it in English. One of the things about this is that there are a lot of ways you could do it correctly. The book will only do one of those ways. So yeah, the way that I have written here is translation, then reflections, then dilations. A lot of people do the opposite, which is dilation, then reflection, then translation. Both work. You just need to make sure you have your x dash, y dash in a particular format. The one that I have printed, we'll have a look at first. If you want to do translation, reflection, dilation, then what you have to make sure is that your x dash and y dash are fully factorized. So you just want to make sure that any common factors are taken out the front. So in this case, they were both divided by 3. Technically, it's already taken out, but we're just going to move it out the front here to be super specific with that. Once everything is in its fully factorized state, you can then do things in order of translation, reflection, dilation. Now, a key thing about this, x and y are independent of each other. So you could do all the y transformations in this order, and then all the x transformations in this order, or vice versa. Or if you really hate yourself, you could intermingle them. But at that point, I wish you the best of luck. Better off just pick one, then do the other in this particular order. So one possibility could be you do your translation of the x first, and then move on to the y. So this would be a translation 1 unit in the negative x, followed by a translation of 6 units in the negative y, followed by a dilation factor of 1/3 along the y, or you can say from the x, whichever you prefer. So x and y independent, translation, reflection, dilation, in that order. I've also got it down here. You could potentially do the y stuff first, the y translation, then the y dilation, followed by the only x transformation, which is that translation. That's one way of doing it. The other way, which is probably a bit more commonly taught, would be the DRT version, which I'll do by hand. So DRT, which means you're doing dilations first, then reflections, then translations. If you want to do it this way, well, let me first just write down the transformations that we had. X minus 1, y dash equals y minus 6 over 3. If you want to do it this way, then you need to make sure that everything you have is fully expanded as far as your x dash y dash is concerned. So obviously the x dash, nothing to do there, there's no brackets involved, but this one you need to expand out. And what that means is you're going to have y dash equals y over 3 minus 6 over 3, which is just 2. When you write it in this particular format, you can now do DRT, which would mean doing your dilate by a third from x. Then you'd look at any reflections, there are none, and then any translations. So this would be translate 2 down, whoops, translate 2 down, and then translate 1 right. As far as wording goes, you could probably get away with this. Maybe actually spell out translate and dilate. But if you wanted to be super specific, you would use the book wording, which would be dilate by a factor of a third from the x-axis, translate by a factor of, sorry, say that again, translate 2 units in the negative y direction, and translate 1 unit in the positive x direction. You can probably see why I didn't write all of that. So if you want to be really sure, bulletproof for your mark, by all means, do that whole thing. But while you're doing SACs, just ask your teacher which one your teacher would prefer or will accept. But okay, as far as why I typically prefer translate, reflection, dilate, part of it is that when you're doing your rearranging, you kind of naturally just do that. So if you look back to the screen share, when we did our rearranging for it, you typically put things over the same denominator anyway. And so it minimizes the amount of further work you have to do if you're doing TRD. And I also think it's a decent habit to have to factorize your terms rather than expand them all out. And the reason why is because it's a good habit for sketching. If you go to the handwritten bit and I create some random, whoops, I shouldn't have factorized it already, 4x plus 2, like this. If you have this function, whenever you have a coefficient on your x, it hides what the actual horizontal translation is. So it's good practice to factorize what you have, taking common factor of 2 out the front to reveal your true horizontal translation. So that's another reason why I recommend doing TRD rather than DRT, but honestly, I just want you to know one correctly, and then you'll be fine with that. Is there anything I should clarify with that approach? I'll pause for about 5 seconds or so. If not, I'll also look at the transformations by recognition approach, which is a bit harder, more freeform. It's less rigorous than that. So we'll touch on it briefly. Okay, so let's see. It's a bit more algebraic. So an example that we have here is just determine a sequence of transformations which would take us from the graph of x squared to the graph of x minus 2, all squared. Something like this, super easy. You can see the only difference between these two things is a shift right by 2. So it will be unreasonable for me to say, yeah, absolutely, do all this to figure out that it's just a shift right by 2. Like, just say shift right by 2 if you can spot it. There are other examples that get more complicated, namely the one that we had a look at. So if you want to use this kind of approach where you just look at the function, a few guidelines to follow are as follows. First, you just want to make sure that all your functions are in their general form. And what I mean by that is like sort of like this. You want it in its factorized-ish form. You want to be able to see all the translation factors, the dilation factors, and all the reflections. From there, just recall that your y transformations are independent to x. And ideally, you'd want to apply your transformations as DRT. But that's more of an algebraic thing rather than like doing it in a particular order. But okay, so determine a sequence of transformations, which gets us from this quadratic to this quadratic. As I said, guideline number 1, make sure you can actually see all your transformations. So this one here would just be a basic example of completing the square. Maybe not so basic, but completing the square nonetheless. Now when you compare f and g together, you can now clearly see the differences between the two. From here, the whole goal is to apply dilations, reflections, or translations to f to make it look like g. Ideally, you do it in this order, and the reason why is because any multiplications to your function will also impact your vertical or horizontal translation term. So if you do your dilation first, then you only have to do one fix-up afterwards, rather than having to do another fix-up later. But anyway. So if we want to go from f to g, starting with dilations, we can see f has a dilate by 3, from the x, and g has a dilate by 4 from the x. So we need to figure out what do I need to multiply f by to make it look like g. Well, that's going to be multiplying by 4 over 3. All right, if you multiply by 4 over 3, the 3's will cancel, and you'll end up with a 4 there. So multiply the entirety of f by 4 over 3. See, remember, it's got to be the entirety of it. This is why we do these first, so we don't mess this up too much. Multiply by 4 over 3. Now you've got this dilation factor well and truly sorted. There were no dilations on the x to speak of, and so we can move on to the next step, which would be any reflections. There are no reflections, so we're happy. This is our new current set of functions. No reflections, happy enough. From there, we can now compare some translations. So first thing we're looking at are the vertical translations. We got 28 over 3 that we currently have. We want to make that look like 12. So we need to figure out, what do I have to add or subtract to this to make it equal 12? Well, just find the difference of those two numbers. If you were to add 8 over 3, you would make it 12. Hence your vertical translation is going to be 8 over 3. And lastly, you would fix your horizontal translation. So you've currently got, where is it? You've currently got an x minus 2. You want it to be an x minus 1. That one you can probably quickly spot. You would just need to shift, shift right by 1 additionally. Wait, no, sorry. We're going the other way around. F to G. This is a right by 2. This is a right by 1. So you need to shift left by 1 to get to it. And so that's exactly what you do. All in all, there's an algebraic approach to doing that. And then you just summarize a list of what you just did, which we started by dilating by 4/3. We translated 8 over 3 in the positive y and 1 unit in the negative x. That's working with the function specifically. If you prefer doing algebra, I've found the point form has been better, in my opinion. Anything I should clarify there? I feel like that one's a bit like harder to wrap your head around, but that's maybe just me. I'll do a screen grab of both of them anyway, so you can use any which one you would prefer as we go through questions. Yeah, okay. If there's no questions, then let's get into it. So I've got a screen grab of it. I will write down 1A and we'll try to do some of this together. Which, by the way, reminder, these are tough questions, quite tough questions. So it'll take you a little bit of time to get used to it, potentially. Okay, we have y equals x squared, and we want to go towards y equals 2 bracket x minus 1 all squared plus 3. X minus 1 all squared plus 3. That's what we're aiming towards. So, using whatever method you prefer, let me know what you might want to do to start.
Would you want to apply the dilation factor to y is equal to x squared first?
Yep. So if we're doing the function notation version, you want to make sure you're doing your transformations in order of DRT. And so yeah, applying a dilation factor. What would that look like as the step?
Like, we can rearrange it using algebra. We can just do it through like recognition as well.
Yeah, sure. I'm just asking like what the actual next step would be. Whichever method you use, I don't mind.
It'll just be y is equal to 2x squared.
Yep, y equals 2x squared. Cool. So this would be using the second approach, y equals 2x squared. Yeah. So already we're getting just a little bit closer there. Cool. So you could even, like as you're doing it, maybe even label what's done. This will be a dilate. Now, another potential pitfall here is you've got to be aware of like what factor that actually is. Dilates in the x direction look different to dilates in the y direction. Do you know what dilation factor this is? If so, what?
Is this like a y factor dilation?
It is, yep. So if I were to write this like using the language of the book, this will be a dilate by factor what?
Factor of 2 in the away from the y?
Dilate factor 2 from the x, it would be. It's a
Oh,
y, it's a y dilation, so you'd say from x. That's fine. Okay, that's first one done. If there's any more dilation factors, we would do that. Otherwise, the next thing would be reflections. So are there any dilations, I guess, or even all reflections left to do for that matter? And if not, what would we move on to?
We're looking translations now.
Yep. No more dilates, there's no more multiplications, no reflections, there's no negatives on the x or y. Moving on to translations. Yeah, you kind of have free reign as to how you want to go about this. You could do these in any order, y first then x, or x first then y. What would they be?
You would first like make it 2 times x minus 1 all squared.
Yeah.
So that like gives you like an x translation in the positive x by 1 unit.
Yep, translate 1 unit in the positive direction of the x, yep. I'll just write shorthand so we can get through it a bit quicker.
And then you just add 3 to the whole function.
Yeah, exactly.
Which gives you like y translation of 3 units in the positive y.
Absolutely. Translate 3 positive y. Nice. And then that just becomes your list. So this specific order, that is the list of transformations that gets you from one to the other. The reason why algebraically we can just shove a x minus 1 into here is because when we're doing this, what we're doing is we're replacing either our y or our x with a new version of y or x. So mathematically speaking, to apply this dilation of 2, what you do is you go from y equals x squared and you transform that to a half y equals x squared, because that's how dilation factors from the x actually look naturally. So you just It's actually a substitution what we're doing rather than just chucking terms in there. You don't have to really know this. This is more so just like, why can we do stuff like this? At every stage, we're just doing a substitution. So this second stage here was just replace x, so it'd be x dash equals x minus 1. So you replace every x, well, sorry, the other way around, wouldn't it? It'd be x equals x dash minus 1. And you replace every x with the x minus 1. That's why that works. Okay. That's pretty much going to be the same idea for all of those. In question 1, we're starting from some untransformed graph and we're going to some transformed graph. Now we're going to go the other way around. Again, you can use either approach, although by looking at it, no, should be similar enough. Okay. All right, the first one, which is going to be, we have y equals, oh, a blurry thing, y equals 5 over, I'll unblur it once I write the whole thing out, x minus 3 all squared minus 7. Now we want to get that towards y equals 1 over x squared. That's our target. So again, using either approach, how might we get from the first one to the second one?
Can we add 7 to the left side?
Yeah, you can. Ideally, if you're doing the by recognition approach, you would do dilations first, then reflections, then translations. We'll do it this way. No, actually, I don't think it'll matter in this case because you're cancelling out the factor anyway. Yeah, this will work. So if you add 7 to both sides, well, if you add 7 to this rather, that will very quickly cancel out that minus 7. Minus 7 plus 7 equals 0. Adding a 7 as far as transformations are concerned would be what?
The translation
Mhm.
in the positive direction of y by 7 units.
Yep. That's it. Nice. All right. Next up, what else could we do?
Can we divide it by 5 to get rid of the dilation factor?
Yep, that's it. 1 over x minus 3 all squared. And that transformation would be what?
Is this factor 5 from the x?
Factor of fifth from the x, this one would be, because you've gone from 5 down to 1, and since it's a y dilation, the number that you divide by is the factor. It's only if it's an x dilation where you would flip it. This one will be a dilate fifth from x. Is that okay? And then lastly, only one thing left to do there. How do we finally make that look like the 1 over x squared that we want? Pretty close. There's only one transformation factor left to get rid of.
We have to shift 3 units in the negative x direction.
Yeah, shift 3 units in the negative x direction, correct. Which would bring this down to 1 over x squared, and that'd be a translate 3 negative x direction. And that becomes your list again. Yeah. Now, this one was lucky being able to do translations first, then dilations. The reason why is because we were zeroing it out every single time. So a further multiplication of a 0 isn't going to actually do anything wrong. In question 3 stuff, it'll become much more apparent why that's an issue, because no longer are we aiming for a 0 on all of our transformations. So any further multiplications afterwards would also affect that term as well. So we'd have to go back and fix it. But under this circumstance, yeah, by all means. Okay, we'll do one more. I guess they're all kind of the same. Linear can be a little bit weird, just by the way it looks, because it's a bit harder to say this is a dilate on the x, or this is a dilate in the y direction or x direction. Even the translation, it's like, is this a shift horizontally or vertically? It's kind of all of it, which is a bit strange. 2x plus 7, and then y equals 3x plus 2. This is where you've got to be a bit more bulletproof with your understanding of transformations as far as like what they're called. The algebra is identical to what you've been doing already, but what you actually label those can be potentially weird. But okay, we're going from left to right. What do we do?
Do we multiply by 3 over 2?
Yeah, multiply by 3 over 2 sounds like a good idea to me. So step 1, multiply by 3 over 2. So it'd be 3 over 2 out the front of. Now, I know you could just chuck it directly in. I would say still put the brackets around it, just so you don't forget that the 7's there to be multiplied as well. So the 2's cancel, 3x, and then 21 over 2. Yep. And as far as, now here's the real question, which is, when you multiply by 3 over 2, what kind of transformation is that?
The dilation
It is.
from the x, I think.
Yeah, from the x. What's the number?
Of that factor 3 over 2.
Yeah. If it's from the x, it keeps the number. That's good. Looks like all these are from the x, huh? Do they even have a single one? I mean, this one you could actually rewrite as from the y. The way you would do that is invert it. So you could say it's a dilate of 2/3 from the y. That's what makes the linear ones a little bit weirder, because they can theoretically be described as either. The reason why you invert it, by the way, is because in function notation, a division by that number is your factor. So this is a multiplication of 3 over 2. You'd have to flip that to an equivalent division. You would do x over 3 over 2, which causes it to flip. That just makes life harder. That's more just an explanation as to why you could do one or the other. But okay, so our dilations are now matching, 3x and 3x. Now we just got to figure out how to get from 21 over 2 to 2.
Subtract 17 over 2.
Yeah, subtract 17 over 2, correct. So you just figure out whatever the difference is between these two numbers, which happens to be 17 over 2. if you were to do y equals 3x plus 21 over 2 minus 17 over 2, y equals 3x plus 2. Now, this thing here was the transformation, and so what does that read? That's a, oh, hang on. How tough is the question? Yeah, this one does have an easy answer and a hard answer, just like the dilation does. What would this be like? Which of those scenarios that I wrote out seems a bit more applicable to what we just did here by putting a minus 17 over 2 where we did? Second, yeah, correct. So this one here, what do we call that as far as transformations are concerned?
The translation by 17 over 2 units in the negative y direction.
Correct, yeah, exactly right. So this will be translate minus 17 onto negative y direction. Now, the reason why I say there's a hard version of this, which is you could write it like this, in which case you'd be replacing your x with a translation such that you get negative 17 on 2, which would mean something like, instead of saying 3x, you would now have 3x minus 17 on 6 plus 21 on 2. And then once you distribute the 3 out of that, you get back to minus 17 on 2, and then it cancels down. And then this would be your horizontal translation to the right of 17 over 6. Don't do that, obviously. That's just for fun. Just to demonstrate how, I mean, even quadratics kind of does this. When you have, like, let's say it was bracket 3x plus 2 all squared, you can take this factor of 3 entirely out of the square and make it a y dilation instead of an x dilation. It's just, at that point, why would you? But okay, that's pretty much as hard as that's going to get. So this one focused on doing things by recognition. I have a few examples of that we obviously had a look at the beginning, so feel free to refer to those. Otherwise, if you feel like the point form would be a bit more appropriate to how you do things, I've got 2 additional examples that you could have a look at from there as well. Yeah, that's about it really. So I guess we'll cap this one off by maybe not solving necessarily, but at least discussing question 4. So we've got this scenario here where we have some cubic equals some other kind of cubic. One's in the full polynomial form, the other's in an inflection point form. And it tells us by equating coefficients, figure out our a and b values for it. Does anyone remember what equating coefficients means? Equating coefficients just means it's usually used for polynomials, although it could be used for any like functions when you have two very similar things either side of each other. It's simply that each term in the function across both sides of the equation need to be identical for those things to be the same. So basically, the x cubed on the left needs to be equal to the x cubed on the right. The x squared on the left needs to be equal to the x squared on the right. So I've got a rough example of a similar thing on the handwritten bit, which is you've got 3x squared plus 2x equals ax squared plus bx. Just by looking at this, every x squared needs to be identical, both sides of the equation, which means a must be 3. Right? Then you have 3x squared on one side, 3x squared on the other side. And then you just compare the next set. So these are the x terms. There's a 2 on one side, there's a b on the other. B is therefore going to be 2. Now that's just an example I made, and that was directly comparable. If it was a little bit harder, like this, ax plus b, suddenly these aren't super comparable anymore. You can't really just, I mean, if you're really good, you can look through that, but there's no like direct immediate in this form, one-to-one that says, this has got to be that, and this has got to be that. A bit harder to see. So with that in mind, we have a very similar thing in question 4. Based on what I've discussed, what do you think you might have to do to solve for A?
Chris, would you have to solve like the equation by like maybe taking like the 2 over to the left-hand side?
Yeah, that could work, right? Divide everything by 2 would at least do some rearranging there, absolutely.
And then maybe would we have to use a like knowledge of polynomial division?
Polynomial division. As in for the left-hand side one, polynomial divide that.
Yeah, yeah.
The only challenge there is polynomial division creates a factorized polynomial, where this kind of looks factorized, but you just got to remember there's plus b out the front, which kind of defeats that, because everything would have to be like in a multiplication sequence. It's kind of broken by this plus b here. So if this did have a sequence of brackets, by all means, you would absolutely rely on your polynomial division, or at least you could rely on your polynomial division there. The more intended solution for this one is to expand this all the way out. Because if you expand this side all the way out, you'll have polynomials that are directly comparable to each other. Right? You're going to have some x cubed term, you're going to have some x squared term, so on and so forth. Just to save a bit of time, I'll get the CAS to expand that out for us, and then sort of show you what that will be like. So menu 3 for expand. We have 2 bracket x minus a. Now, of course, I've got an a already assigned. Let me kill that for a second. It's like 3, 2 times x minus a. Oh, I've got a b as well, don't I? I'm pretty sure I do. Yep. Okay. Kill the b. And now we're sorted. Okay, so what this tells us is we have, whoops, it's supposed to be cubed, not squared. That's a bit better. Now that we have it in this form, we can actually directly compare that to what we have in the actual book. So you can see there was a 2x cubed in the book version, there's a 2x cubed in our version. Nothing to compare. There's a minus 12x squared here, there's a minus 6a x squared here. So in that case, a would have to be 2 for those two to be equal to each other. And you would just go down the list until you solve your a's and b's. If that's not super clear, feel free to stay behind. Otherwise, this is end of class. So I'll hang out. Otherwise, take care.